Kinetic energy, we saw a couple days ago, is defined as the energy of motion. Anything that's moving has kinetic energy. Whether we're talking about an electron, something as small as an electron going around a nucleus of an atom, or whether we're talking about a train rolling down the track, okay, kinetic energy is the energy of motion of any of those objects. We can describe that kinetic energy by a simple formula that you've seen before. Ek is equal to 1/2 mv squared. What does m stand for? Yep. Mass, good. What are the units that we use for mass there, Eric? Yeah, good. Kilograms. And what does v stand for? Bo? Good. Speed. And what are the units that we use for speed there? Wilson? Good. Meters per second. So remember, if you're in grams, you got to convert to kilograms. If you're in kilometers per hour, you've got to convert to meters per second. Let's do a quick conversion there, okay? From kilometers per hour to meters per second. Let's say we've got 72 kilometers per hour. We want to convert that to meters per second. What do we do first there? There's really two simple conversions to do here, right? Okay, not one difficult conversion. It's two simple conversions to do. The first one we've got to do is convert kilometers to meters. How many meters in 72 kilometers? Yep. No. 72,000. Right, it's multiplied by 1,000. Kilometers to meters multiplied by 1,000. That's what we're doing first, right? Not kilometers per hour to meters per second, but rather kilometers to meters. 72 kilometers is 72,000 meters. How many seconds in an hour? Yep, 3,600. So it's 72 kilometers per hour is the same as saying 72,000 meters per 3,600 seconds. We divide those two, we end up getting 20 meters per second. So if this was the question, this was the data for our question, then we would plug that value 20 into V there, solve for Ek. What are the units for Ek, by the way? Hayden? Joules, yeah. And is Ek, kinetic energy, is that a vector or a scalar? Vector or scalar? Sadie, is that a vector or a scalar, kinetic energy? Good, it's a scalar. In fact, any kind of energy is a scalar. So if I ask that question in about 2 minutes for potential energy, is this a vector or a scalar? The answer is also scalar. And the answer for the units is also joules. All right, let's talk about potential energy for a second. There are lots of types of stored energy, lots of types of potential energy. Two that we talk about in Physics 20 are gravitational potential energy, and then we've got spring or elastic potential energy. The gravitational potential energy is the energy stored in an object due to its height. The spring or elastic potential energy is the energy that's stored in a spring or an elastic, or something like a spring or elastic, stretched or compressed. The symbol for both of them is EP. What are the units for both of them? Told you I was going to ask you this question, right? What are the units for both of them? Good. Units are joules. Are both of them vectors or scalars? If kinetic energy is a scalar, then potential energy is also, Aiden, going to be a scalar as well. The equation for gravitational potential energy is mgh. M is mass in kilograms. G is, that's a constant, right? Its value is 9.81, right? It's always 9.81. We're going to make it positive here because potential energy is a scalar. So just drop the negative sign for G in this case. H stands for what? It's the height. It's the height above whatever we want as well, right? Right now, the height of the pen above my pen, above the ground, is about 1.5 meters. So we would plug in a value of 1.5 meters if we wanted to find the potential energy of the pen relative to the ground. But if we want to find it relative to my hand, what value of H would we plug in? What's the height of the pen above my hand? 0, right? So that means that the potential energy relative to the ground is something. Relative to my hand, it's nothing, because m times g times 0 is nothing. What was the equation for spring or elastic potential? And this is what we really focused on yesterday, right? Spring and elastic potential. You guys remember? Check your data sheet if you don't. Josh? Right. E is equal to 1/2 kx squared. You remember what x stood for? It stood for a term that we've heard before, but it meant something different. Krista? Good, it's displacement. But it's not displacement how far it goes, right? It's not how far it travels. I could throw the pen across the room, and that would be displacement, but that would be displacement delta D. Okay, we're talking about displacement x. What does that mean exactly? Displacement x. Really? Yeah, good. It's how far it's stretched or how far it's compressed. If you're talking about an elastic, it probably wouldn't be squished or compressed, right? Probably just more stretched, like you said. But if you're talking about a spring, it could be stretched or it could be compressed. And whichever it is, it doesn't matter. The amount that it's compressed or stretched is your displacement. What units would we use for that? What units are we always going to use for displacement, whether it's delta D displacement or whether it's x displacement, Mason? What units do we use for x? Good. What does K stand for? Pardon? It's the spring constant or the elastic constant, and it really is just a measure of how stiff the spring is. Right? If we have a really stiff spring, it's got a high spring constant, and it can therefore hold a lot of potential energy. If it's a loose spring, it's not very stiff at all, then we've got a low spring constant, and it can hold not a whole lot of potential energy. What would the units for spring constant be? Fraser? Good. It's newtons per meter. Now, sometimes we didn't have the value of the spring constant K. Sometimes we needed to find it to put it into this equation. To do that, we used something called Hooke's law. Hooke's law says that F is equal to Kx. In other words, the force on a spring is related to how far the spring is stretched, okay, which is kind of odd compared to what we've done so far this year. Right? So far this year, force has been a force. Okay, if the force was 20 newtons, then it stayed at 20 newtons through the whole problem. Okay, now it doesn't. Now, if I take that spring and stretch it a certain distance, maybe it takes 20 newtons. But if I stretch it a little bit further, maybe it takes 30 newtons or 40 newtons. Okay, the further you stretch it or the further you compress it, the more force is required. F is related to x. Now, what we often do here is take that equation and rearrange it to solve for k, get F over x. And then we take that value of k oftentimes and we plug it into that equation for the spring or elastic potential energy. All right? We had 5 questions for homework last night. A number of you worked on them during scheduled help yesterday, and I think got them done in class and had an opportunity to ask me questions as you were doing that. Okay, for those of you who didn't get them done in class, or those of you who weren't here for scheduled help, are there any issues with these? 1 to 5. Brennan? Number 4? 5? 4 and 5? Is that it? Okay, let's take a look at number 4. It says a spring has an elastic constant of 4.4 times 10 to the 4 newtons per meter. What's the change in elastic potential energy? Notice here they're not asking us for elastic potential, EP. They're asking us for the change, which is not EP, it's delta EP. And so it's not crazy hard to find delta EP. We just have to recognize that we're not looking for that EP, that equation, or that variable that appears in the equation on our data sheet. The spring is stretched from 12.5 centimeters to 15 centimeters. Let's write down some givens here, okay? We've got a spring constant of 4.40 times 10 to the 4 newtons per meter. We've got a couple strange units here as well, right? In centimeters, we want to convert to meters. We're going to say x1 is 12.5 centimeters or 0.125 meters, and x2 is equal to 0.150 meters. x1, the first displacement, x2, the second displacement. You could have called them xi and xf. Doesn't really matter. Now we want to find the change in potential. What you don't want to do is this. Why not? If EP is equal to 1/2 kx squared, then why can't delta EP be equal to 1/2 k times delta x squared? Travis? Because it's squared. That won't work for you. You can try it, but it's not going to work for you, I promise. So let's do this. Let's get EI. That's going to be equal to 1/2 of k times xi squared. We should have called this xi and xf. 1/2 of 4.4 times 10 to the 4 times 0.125 squared. Let's get a value for that. Thank you. We get 343.75 joules. Thank you, Alex. Let's get EF now. It's also going to be 1/2 kx squared, but this time x is going to be a different value. It's 1/2 of 4.4. Hey, why can't I use the same k? We're in a different situation now. Why can't I use the same value of k, Aiden? It's the same elastic or the same spring, right? K doesn't change for a particular spring. Now, we move on to another question. K is going to be entirely different. But within a particular question with one particular spring, it isn't going to change. It's going to stay the same. So 4.4 times 10 to the 4 times this time 0.15 squared. Somebody have the value for that? We can always go to Alex here, but we don't want to always have to go to Alex for this. What do you have? 495? 495, did you say? Even? Or point something? Okay. Anybody else have that? 495 exactly? Okay. So we're looking for the change now, the change in potential energy here. The change in potential, we can still say it's delta E, but we're not going to say it's 1/2 k times delta x squared. Rather, we're just going to say it's final minus initial, or 495 joules minus 343.75 joules. And that's going to give us 151.25, or 1.51 times 10 to the 2 joules. 151 or 1.51 times 10 to the 2, either one of those works. Better? Say that again. That's a good question. Yes, I think that it would. Yes, I think that it would work. As Brendan's question is more of a mathematical thing as opposed to a physics thing, but it's a good question nonetheless. He said basically, could you do this? Yeah, I think that should work. What you can't do is say, right there. Okay, does that make sense? Did you try it this way, Brendan? Did you got the right answer? Okay, good. Okay, that's fine. It's, but some people are going to have a little trouble with that mathematically, seeing why this is the same thing and why it's not the same thing as this. And I don't really want to go into huge detail to explain why that's the case. But if that makes sense to you, then go ahead and use that. All right, our other question was number 5. Let's take a look at that one now. This one says, when a spring is stretched 0.400 meters from its equilibrium position, its elastic potential energy is 500 joules. What's the force required to do this? Okay, we'll worry about B a little bit later on here. We've got X is 0.400 meters. We've got EP is 500 joules, or 5.00 times 10 to the 2. We're looking for the force that's required to do this. Okay, normally, if we need to find K, we're going to use F is equal to K times X to get it. Here we can't, because we're looking for F. Here we're going to have to use F is equal to K times X to get F. I know what X is, I don't know what K is. Going to kind of work backwards here to what we usually do. Instead of using this equation to get K and then plugging it into the potential energy equation, I'm going to use potential energy to get K and then plug it into the force. So let's say K is EP I should say, is 1/2 kx squared. Let's take the half over by dividing, or the 2 over by multiplying. It doesn't matter which way you do it. Take the 2 over by multiplying this time. 2EP over x squared equals k. So it becomes 2 times 500 over 0.400 squared. It's 1,000 divided by 0.16. 624. 625? Even? Even? Okay, 625 newtons per meter, thank you. Now we're going to plug that in here, 625 newtons per meter times 0.4. Yeah, go ahead. Is there a mistake there? Okay, 6,250. 6,250 times 0.4, which is going to give us 625 times 4, 1250, 2,500? Is it 2,500? 2,500 newtons, or we're going to round that to 3 digits, 2.50 times 10 to the 3 newtons. Is that okay? All right, question B says if the force causing the stretch is changed to 1,000 newtons, how much change in elastic potential energy results? Well, we want to find EP is equal to 1/2 kx squared. This is a tricky question right here. We want to find EP is equal to 1/2 kx squared. We already know what k is. We found it using this equation before, so it's going to be still 6,250. That's not changing just because we're stretching it further. But we don't know what x is. We're going to use the force equation this time to find what x is. X is equal to F over k. The force is 1,000 newtons this time, divided by 6,250. What's 1,000 divided by 6,250? It's 0.16. Exactly. Okay, thank you. 0.16, and that's going to be meters. Well, now that we have x for this new force, we're going to plug that in here, 0.16. We're going to square it, and then we get a value for EP there, whatever that works out to be. So understand here, whenever we do one of these questions, again, we're not going to change the value of k. Anything else can change. Force can change, x can change, EP can change, but k doesn't change. Once you get it, you can use that for the whole question. And you can see that we've done that here. Okay, we had to find EP using we had to find k using 1/2 kx squared. And then we plugged it into our force equation. Then we switched the question around completely, except for the spring. So my force was different. My displacement was different. My EP was different. But my k stayed the same. That was my one constant through this problem. And that's how I was able to get question B. How many people got B? The tough one. How many people got that one? Okay, good. If we think we're pretty good at these questions, let's try one more example here. This one says on 6.6 on 304, this one says, a man on a trampoline has a mass of 75 kilograms. At the instant he first touches the surface of the trampoline at its rest position, he's descending with a speed of 8 meters per second. Okay, so when he touches the trampoline, he's moving at 8 meters per second downward. Now, at his lowest point, when he starts compressing the trampoline and he reaches his lowest point, he's 0.650 meters below the trampoline's rest position. We want to know the kinetic energy of the man when he first touched the trampoline. That seems pretty straightforward, right? We got his speed, we got his mass. We want to know if all of the man's kinetic energy was transformed into elastic potential, what the elastic constant for the trampoline was, what the spring constant for the trampoline was. I don't know about you guys, but I've jumped on a trampoline before as a grown man, but usually when I do that, it's with one or both of my kids. It seems a little odd to me that this guy is just jumping on the trampoline all by himself, this 75-kilogram man, but maybe he just likes to have fun. I don't know. The guy's mass is 75 kilograms. His speed when he strikes the trampoline is 8.0 meters per second. Let's worry about the potential energy thing later on. Let's just find EK right now, question A. EK, when he strikes the trampoline, is 1/2 m times v squared. So it's 1/2 of 75 times 8.0 squared. Now, you know that as he stretches that trampoline, he's going to slow down, right? That's only logical. If he stretches the trampoline, eventually he comes to a stop when the trampoline is fully stretched. So he must be slowing down in that process. We don't care about that. Right now, at the beginning of this problem, he's moving at 8 meters per second, so that's what we care about. 8 squared is 64. 64 times 75 times 1/2 is what? 2,400 joules. I'm sorry? I did, though. I got 4,800, and then I multiplied it by half, yeah. So we get 2,400 joules, or rounded to the correct amount of digits, it would be 2.40 times 10 to the 3 joules. All right, question B says now, if we assume all of the kinetic energy gets converted to potential energy, and that's where, I mean, really, if you think about the trampoline and its stretching, where does the energy come from? We know that the potential energy in the trampoline is what propels you upwards. Okay, you have to have potential energy to be propelled upwards. But how did you get it stretched in the first place? Where did you get that potential from? Well, it came from the kinetic as you fell downwards. So that kinetic energy has to be converted to potential energy. In other words, EP is equal to 1/2 kx squared. We know the value of EP. It's the same as the value of EK that the guy had when he began to stretch this thing. We're looking for the elastic constant K. So let's rearrange that. Let's take the 2 over by multiplying, or the 1/2 over by dividing. Let's divide it by x squared. Do I have to square root anything here? Not unless you're solving for x, you don't. Okay, k is not squared, so there's nothing to square root here. It becomes 2 times 2,400 divided by x, which we said was, what is x? 0.650 meters. 0.650 meters. So we've got 4,800 divided by 0.650 meters. 1.14 times 10 to the 4. Thank you, Josh. And the units for that would be, of course, newtons per meter. Oh, wait a second. Made a mistake there. It's not divided by 0.65. It's divided by 0.65 squared, right? Don't forget to square that x on the bottom. Oh, that was the right answer? Okay. Okay. So basically, you didn't listen to me. You did what was right instead of what I told you to do. Good. What did you get again there, Josh? What did you have again there? Thank you. You know how I caught that little mistake that I had made? Not because I noticed that it was supposed to be squared and that I didn't square it. I noticed that on the bottom, if I didn't square that, I had meters. But I noticed on the top, I had joules. Joules per meter is not the unit for spring constant, right? Newtons per meter is the unit for spring constant. So I knew when I saw that I had done something wrong. It can't be joules per meter if it's newtons per meter. So as it turns out, it's joules per meter squared. Now, you might have a tough time seeing, okay, how is that the same thing as newtons per meter? Don't panic about that right now. Bottom line is, it can be the same thing as newtons per meter, and it is. Okay? Joules per meter can't be the same thing as newtons per meter. Yeah, yeah. We know that spring constant is measured in newtons per meter, right? Well, the equation that I used to find spring constant in this last one was 2EP over x squared. But I didn't square x. I only went 2EP over x. So that would have given me joules per, well, x squared is joules per meter squared. But I had joules per meter. Well, I know that this can't be equal to this. If it has the same denominator, then the numerator has to be the same as well. So that told me that I had made a mistake, since I had gotten joules per meter for the spring constant there. Now, when you do it properly, like Josh did, he's going to get joules on the top over meters squared. Now, that may not look like newtons per meter, but it is the same thing as newtons per meter. Okay? If you don't trust me on that, we can say a joule. Okay, that comes from either our potential energy equation or our kinetic energy equation. Let's say potential energy. It doesn't matter which one we use. Kilograms times meters per second squared times meters. So that gives us kilograms times meters squared over second squared, right? Over meters squared. That cancels. Well, now we've got kilograms per second squared. That's still not the same. Still doesn't look like a newton per meter. But if you take a look at a newton, F is equal to m times a. That's a kilogram times a meter per second squared. So this becomes kilograms times meters over second squared over meters. A kilogram per second squared is equal to a kilogram per second squared. Don't panic about that, guys. I only did that because Josh, or because Travis was asking me the question. But they are the same thing, though, right? Whereas joules per meter is not the same thing. Okay, try these three, please. Okay, guys, let's take a look at question number 3 here. It says, it's estimated that the meteor created by the meteor, I can't say this. I don't know why this is such a tongue twister. It is estimated that the meteor that created the crater shown in figure 6.21 on the previous page had a radius of 40 meters. That's a pretty big meteor. Okay, you see one of those coming towards you, you better run fast. A mass of approximately 2.6 times 10 to the 8 kilograms and struck Earth at a speed of about 72,000 kilometers per hour. What's the kinetic energy of the meteor at the instant of impact? Well, we've got the mass here is 2.6 times 10 to the 8 kilograms. We've got the speed as well, although the speed, we don't want to put it in kilometers per hour, we want to put it in meters per second. So we're going to say 7.2 times 10 to the 4 kilometers per hour. We're going to multiply that by 1,000 to get meters per hour. Then we're going to divide it by 3,600 to get meters per second. We end up getting 2.0 times 10 to the 4 meters per second when we do that. All right, multiply by 1,000, divide it by 3,600. We want to find its kinetic energy at that point. EK is equal to 1/2 m times v squared. 1/2 of, what do we get here? 2.6 times 10 to the 8 times 2.0 times 10 to the 4. Don't forget to square that. And let's use brackets there, okay? On your calculators, let's make sure we use brackets. When we do the math there, we should get 5.2 times 10 to the 16 joules. Now, that's a lot of energy. How much energy is it exactly? Well, they talk in question B about kilotons or about tons of TNT. When we have large amounts of energy like this, for whatever reason, we always are related to TNT. If you ever hear of a 20 kiloton bomb, like a nuclear weapon, then it would be the equivalent destructive power of 20 kilotons of TNT, 20 kilotons of dynamite. The first bomb that was dropped on Hiroshima, the first nuclear weapon ever exploded in wartime other than testing, okay, dropped in Hiroshima, was about 15 kilotons. Okay, the bomb that was dropped on Nagasaki, which was a few days later, was about 20 kilotons. So a little bit more destructive. I mean, you think about that. Hey, you drop a 15 kiloton nuclear weapon on Hiroshima. That's the equivalent of about 15,000 tons of TNT. Okay, that's a lot of energy. That's a lot of destructive power. Okay. The bombs that we have now, the nuclear weapons that we have now are completely different. They're based on a process called nuclear fusion, and they're in the range of 10 megatons, so about 10,000 kilotons compared to what we have there. Just out of curiosity, guys, I said Hiroshima was about 15 kilotons. The largest human-made explosion ever prior to Hiroshima, okay, the largest man-made explosion ever in the history of the world prior to the nuclear bomb dropped on Hiroshima was about 3 kilotons compared to 15 kilotons, which was the atomic bomb that was dropped on Hiroshima. Do you know what that was? Do you know where that was? There was a 3 kiloton explosion that took place on December 6th, 1917, during the First World War in Halifax, yeah. Yeah, so the largest man-made explosion ever prior to World War II, and the atomic bomb that was dropped on Hiroshima was in Halifax, and it was by accident. It wasn't on purpose, but 2 ships collided in the harbor, and one was loaded with literally tons and tons and tons of dynamite, and that's what happened. Here, let's see what this is. I think we're going to find that this is a bigger explosion than the Halifax explosion was. But this wasn't man-made either. This is a natural explosion, right? Okay, let's figure out what it was. We have 5.2 times 10 to the 16 joules. One ton of TNT releases this much energy. So let's say I want to find the number of tons of TNT. It's 5.2 times 10 to the 16 joules. We divide that by 4.6 times 10 to the 9 joules. And we're going to end up getting what? 1.1 times 10 to the 7 joules. Oh, sorry, 1.1 times 10 to the 7 tons. What's 1.1 times 10 to the 7 tons? That would be about 11,000 kilotons. So the Halifax explosion was about 3 kilotons. The bomb that was dropped on Hiroshima was about 15 kilotons. The bomb that was dropped on Nagasaki was about 20 kilotons. An atomic bomb that we have now, a nuclear fusion bomb, would be about 10,000 kilotons. This meteor released as much energy as about the most powerful nuclear weapon that we have on the face of the Earth now. That's why we think that the dinosaurs were destroyed by a meteor that crashed in the Gulf of Mexico millions of years ago, because it releases so much energy. It's the equivalent of an incredibly powerful nuclear weapon. Yep. How much of Earth would it destroy? Well, there would be a huge blast radius for that. Now, having said that, we have this impression, we have this kind of sense that when a nuclear bomb is dropped on, say it's dropped on the United States, a nuclear, the Russians or the North Koreans or whoever launched a nuclear weapon on the United States and it would destroy the United States. It wouldn't. Okay, it wouldn't. A nuclear bomb would destroy a city. Okay, a nuclear weapon would destroy New York City or it would destroy Los Angeles. But if it was dropped on Los Angeles, New York wouldn't even feel it. Okay? I mean, geologically it might be felt, but you're not going to notice it in New York City. The world could be destroyed by nuclear weapons, but it would have to be lots and lots of weapons. This would create a large blast radius, but it's not like it would destroy a country. Okay? If something like this hit a city, it might destroy a city, yes. Like Calgary would be probably pretty much wiped off the face of the Earth, pretty much, if a meteor this size hit it. But the good news is, the good news is we can usually see them coming. Okay, we know when it's, nowadays, if something like that was going to come, we'd know it was coming. The bad news is we can't really do anything about it. But we'd know that it was coming. Unless you watch, what was that movie with Bruce Willis? No, not Die Hard. It's about the asteroid. They went up to the asteroid and then they blew it up. And what was it called? Armageddon, that's right. Once you watch Armageddon, then science on that is a little dubious at best, though. Okay, does that make sense? Is there any other questions with 1 or 2 here? That's good? Let's take a look at another topic here now that's related certainly to what we've been doing over the last couple of days. This is the topic of work. We're going to define work as the change in energy that's experienced by an object. The energy gained or the energy lost that's experienced by an object. So if you're jumping on that trampoline, as we saw in the question that we had a little while ago here, and you lose a certain amount of kinetic energy as you hit the trampoline, then the trampoline has done work on you. If you climb upstairs and you gain a certain amount of potential energy, then you've done work against gravity. Okay, if you slam on the brakes in your car and you come to a stop, then friction has done work on your car because it's changed the energy of your car. Okay, the amount of energy that is changed, that an object experiences, the change in the amount of energy that an object experiences is the work that's done on that object. The work depends upon 2 things. If you think about that, how do you change an object's energy? Right now, Lane's desk isn't moving, right? It's sitting there. What's its energy right now? Nothing. Okay, if we don't take into account its chemical energy, it doesn't have any energy. It's not moving, it has no kinetic, it's on the ground already, it has no potential. So its energy is 0. Now, how do I get it moving? How do I give it energy? How do I change the amount of energy that it's got? Well, there's two things that I got to do. Number one, I've got to push it. Okay, there's no way this desk is going to gain energy unless I push that desk. So what's one of the things that's required for work to be done? One of the things that's required for energy to change? Force. Okay, you need a force. When you apply a force, you cause the object's kinetic energy to either increase or decrease. Doesn't matter which one you're doing, you're changing it. Yeah, if I push on his desk, I cause it to start moving, I'm increasing its kinetic energy. I'm doing work on it. If it's already moving and I stand in front of it to try to stop it, and I apply a force to do that, then I'm decreasing its kinetic energy. I've still done work on it. Now, the other thing that's required, besides just a force, is movement. If I apply a force on this wall doesn't move. What have I changed the kinetic energy of that wall by? The kinetic energy was 0. I push it, it's still 0. So I've changed it by nothing. I haven't done work on the wall. I need movement. Not only do I need to push on the wall, I need to move the wall to do work on it. Not only do I need to push on the desk, I need to move the desk in order to change its kinetic energy and therefore do work on it. So we need a force and we need displacement. We need movement. Now here's the thing. The force and displacement have got to be parallel to each other. Okay, if I push on this desk parallel to the ground, it's going to move parallel to the ground. The force was parallel to the movement. But if I push on the desk down this way, I'm not causing movement. So I haven't done any work on it. Even if the desk is sliding along the floor and I push down on it, I'm not going to change its speed that way. So if I don't change its speed, I'm not changing its energy. And if I'm not changing its energy, I'm not doing work on it. So it's not enough to apply a force. We need movement. But it's not enough to have just movement. We have to have the force and the movement in the same direction, or parallel to each other. In other words, I must be causing the movement, or I must be restricting the movement, one of the two. I must be affecting the movement. And if the desk is moving horizontally and I push down on it, then I'm not affecting the movement. So these are the two things, but they're tied together. We need force, we need movement, and we need the force to be causing or to be affected by, affecting the movement. The object is moving this way, and I push this way, there's no work done. If the object is moving this way, and I push this way, well, it's still not parallel, but at least I am affecting the movement somewhat with a component of my force. And that's why in that case we'd have to not use the force that we have there, but rather a component of it. Let's use what we just learned, put it together, and get an equation for work here. Work, capital W, is equal to delta E. Work is a change in energy. That's the definition of work, right? That's easy. Work is equal to delta E. Change in kinetic, change in potential energy. But we also know that work is equal to, well, if force is required and displacement is required, it's equal to a force times displacement. Now we assume that those are parallel to each other. If they're not parallel to each other, we have to find a component of the force, which ultimately ends up meaning that we're going to use the cosine function to do that. So the nice thing about this is if you do need to find a component, the equation is going to reflect that for you already. You don't have to go about analyzing it using vectors because the equation already has that component added to it for you already. Work is equal to the change in energy. It's equal to F times the displacement times cosine theta. What does F stand for? The force. What does D stand for? The displacement. What does theta stand for? What angle? You're right, it's an angle, but what angle? Yep. The angle that you're pushing it? Almost. It's the angle between the force and the displacement. Okay, for instance, here's a wagon that we're pulling right here at an angle of 20 degrees. The angle I would use there, FD times cosine theta, the angle that I would use there is 20 degrees. Because if I'm pulling it at 20 degrees and it's moving at 0 degrees, the angle between the way that I pull it and the way that it moves is 20 degrees. Make sense? Let's say I've got a hill, though. I'm pulling this object up the hill, parallel to the hill, at an angle of 30 degrees. What angle would I plug into this equation for this one? 0. Good. Fraser, why is it 0? Yeah, because theta is the angle between the way that it moves and the way that I'm pulling it. Which way am I pulling it? 30 degrees. Which way is it moving? 30 degrees. What's the angle between the way that I pull it and the way that it moves? 0. So W is equal to delta E, the change in energy, but it's also equal to the force times the displacement times cosine theta. Now, most times, what's the situation? Most times, we pull it this way, and it moves this way. What's the angle there? If I pull it to the right and it moves to the right, what's the angle? No. 0. If I pull it right and it moves right, the angle between the way that I pull it and the way that it moves is 0. I want you to do this on your calculators really quickly here. Go cosine 0. What do you get? 1. So when the angle is 0 degrees, which it is most times, the equation becomes F times D times 1. In other words, it becomes F times D. That make sense? So if you're pulling it and it's moving and they're the same direction, you can just drop the cos theta if you want, because cosine 0 will equal 1, and therefore F times D times cos 0 will equal F times D. Yep. What do you mean what it is? You won't learn it in physics class. You might learn it in math class, I'm not sure, but you won't learn it in physics class, no. Okay? I was going to say this is the world's easiest question. Not exactly the world's easiest question, but it's close. We want to find the work done here. We know that work is equal to delta E. Well, that's not going to help us because we don't know what the final or initial energy is. But we know that W is also equal to F times D. Since the angle between the way that it moves and the way that I pull it is not 0, I've got to tack on the cos theta. If I pulled it to the right and it moved to the right, I could drop the cos theta. If I pulled it at 25 degrees and it moved at 25 degrees, I could drop the cos theta. But here I'm pulling it to the right, it's moving at 25 degrees. We're going to say the force is 150 newtons, the displacement is 25 meters, and the angle, of course, here is cosine 25 degrees. 150 times 25 times cos 25 equals what? 3,398? So we're going to say 3.40 times 10 to the 3. I said newtons for that. That's wrong. What would it be? It'd be joules, right? Because work is a change in energy, so it's going to be joules. Here's your homework. Page 294. We got our practice problems here on 294. Okay? Let's make sure those are done for tomorrow, please. Have a good night, everyone. Oh, by the way, we're going to have a quiz tomorrow on kinetic and potential energy, okay? Quiz on kinetic and potential energy.